In this video, we're going to be talking about how to factor using difference of squares or when to recognize difference of squares. So first, going over the steps, we need to make sure we have an actual difference of squares, meaning we need to have two terms and we need to have a subtraction sign. So if we have addition, it's already a no-go. But also we need to make sure that we can take the square root of both terms. So if those aren't met or those aren't true, we don't have difference of squares and we'll have to factor it some other way. Then we're going to be using the following rule to factor. Anytime we have subtraction with two terms that we can take the square root of, the two factors are going to be the square root of the first term. So think about this as like what times what would give me a squared. That would be a. That's going to be the first term in both factors. What times what would give me b squared. I'm going to ignore the negative in the middle for a second. And that would be b. And then in one of your factors, you're going to have a plus, and in the other, you're going to have a minus for every single difference of square polynomial. Then you can check your work by distributing. So if I were to distribute this, a times a is a squared, a times negative b is negative ab, b times a is ba or ab, it doesn't matter. And then b times negative b is negative b squared. Even though I wrote these different, they're exactly the same thing. So these are going to cancel, leaving me with a squared minus b squared. All right, let's try some examples. Number 1, I have a subtraction. A squared can be factored, or I'm sorry, a squared can be, I can take the square root of it, because a times a gives me a squared. I can take the square root of 4, because I get 2. So my two factors are going to be a, and 2, and 2, and then I put a plus and a minus. Does not matter the order in which you write it. It could be a minus 2 and then a plus 2, or how I wrote it here. That is it. That's all. For number 2, same thing. N squared, I can take the square root of it because n times n gives me n squared. 64, the square root of that is 8. So n, 8, plus minus. Again, the order does not matter. For number 3, I have a minus. 81, the square root of that is 9. For x squared, x times x gives me x squared, so I can do that one. But because these are switched, I have my variable term last. I'm going to follow that. So I'm going to do 9 and then x, and then 9 and then x. If you switch it so that the variable is first, you can do that. You just have to remember that this is 9 minus x. So if you switch it around, it would be negative x plus 9, not x minus 9. That'd be two different things. So just be careful with that one. Looking at number 5, k squared, I can take the square root of it because k times k equals k squared. 25, the square root of that is 5. However, this has a plus. So that means I cannot do the difference of squares since this is not different. So this is prime. For number 6, the square root of 1 is 1. Now I have a variable and a coefficient, still the same thing. The square root of 49 is 7. And the square root of y squared is y. So now you have a variable and a coefficient instead of just one. Sometimes that will happen. For number 7, the square root of 9 is 3. The square root of b squared is b. The square root of 100 is 10, and I'm subtracting. I can do this. So 3b and 10, and then plus minus. Once you get the hang of this, it's really looking for, is it a square root? Does it have a square root or not? We'll do one more on this page and then jump to the next one. For number 11, I can take the square root of 4, I can take the square root of h squared and g squared and 25, and I'm subtracting. I'll just have more variables than I had before, which is fine. The square root of 4h squared would be 2h. The square root of 25g squared would be 5g. So 2h, 5g, plus minus. The hardest part about this is really finding the square root of these numbers. Right? Now we have a few that have an exponent of 4 and an exponent of 6. So I'm going to show you how we would do this, because it's the same way, it's just a little different. So the square root of 81 is 9, we know that much. The square root of 25 is 5. For n to the 4th, this is really for any exponent that has an even exponent. If it has an even exponent, it means it can be divided by 2. You are going to really divide the exponent by 2, and that would be the equivalent of taking the square root of it. So the square root of 81 is 9. If I divided n to the 4th by, I said by 2, but I meant like n squared. Divide that by n squared, and I'm left with n squared and 5. Now, I'm going to make up an example really fast. Let's say you break it down into your difference of squares, or DOS. I'm going to start calling it that, DOS. Let's say you get some factor where it's like 9n squared minus 16. Now this is not the case for this one because 5 cannot be broken down anymore. However, if you got an answer that was like what I just wrote in red, 9, I can take the square root of. 16, I can take the square root of. That means I'd have to keep going. I'd have to break this down again. And you'd end up with 3 terms. So I would just put the random one out front instead of just 2. Sometimes that will happen. Just be mindful that if you still have something that's squared and you have numbers that you can break down, take the square root of, you have to keep simplifying as much as possible, or you have to keep factoring. Okay, I'm going to do 18 before I do 17 just because it's another 4 example. 4 I can take the square root of, 25 I can take the square root of, p to the 4th, because it's an even number, I can divide that by 2, and I'd be left with p squared and 5. And again, if 2 or 5 were numbers that were perfect squares, like I could take the square root of either one, I'd have to keep simplifying, but that is not the case for this one. For number 17, 16 is a perfect square. I can take the square root of it. 6 is an even power, so I can divide it by 2, leaving me with k to the 3rd and 4. Now in this case, if it was k squared and 4, then I could keep breaking it down. So let's say I got an example that was k to the 4th and 16. Well, that would give me k squared and 4. But k squared and 4 can be broken down again. Wow, I don't know what happened there. Squared plus, there we go. So that would be an example that we would have 3 terms instead of 2. Those are all hypothetical because that's not actually what happened, but if it did, that's what we would do. For 19, 121 is a perfect square. You may have to list out or go through what all your perfect squares are, but 11 times 11 will give you 121. R to the 6, I can divide the 6 by 2, and 1 is a perfect square. So 11 r to the 3rd minus 1, and then plus 1. We're just going to do a couple more. For these examples, it's not just dose. Now you're also working with GCF. So you have to look and make sure you cannot factor out of GCF. Really, moving forward, anytime you have 2 terms in a polynomial, you're doing one of 2 things. Either factoring out of GCF or factoring out dose, one of 3 things. Or you might be doing both. So in this one, I can take out a 2. So when I take out 2, remember, I'm dividing. I'm left with n squared minus 36. N squared is a perfect square, n and n. 36 is a perfect square, 6 and 6. So that becomes 2 times n plus 6 and n minus 6. You can either do the double parentheses or just leave it as 2 times n plus 6 and n minus 6. So it's the same process, we've just added a step. Jumping down to number 25, I see that both of them I can divide by 4. I'm sorry, I did that problem already in my head. You could list out your factors. So let me do that really fast. I'm sorry, not 4, 6. So the highest number I can take out of both is 6. Which would leave me with 4a squared minus 9b squared. Well, now I have perfect squares because 4a squared, 9, and b squared are all perfect squares. So that would leave me with 6 times 2a minus 3b and 2a plus 3b. Let's do one more. For number 29, I see 36 is a perfect square. I see 9 is a perfect square. But p to the 3rd is not an even number. So I would say it's prime. But I can take numbers out for a GCF. I can also take p out of both for a GCF. So let's see what happens when I do that. The highest number I can take out of both is 9. The highest number of p's I can take out of both is 1. So when I divide both of these by 9p, I'm left with 4p squared minus 1. Now, looking at it, 4p squared and 1 are all perfect squares, so I'm going to be left with 9p times 2p minus 1 and 2p plus 1. You will now have time to practice factoring using notes and GCF. There might be some mixture of those, so just be careful with those.